from the meeting while recording. Okay, some message was there. Okay, that doesn't matter. If somebody is remote, please rejoin. And if you are, I am unable to join you, please give me a call on my number so that I can let you in. Okay, so that was about PV diagram we were discussing. So 1 to 2 was your compression stroke. 2 to 3 is your combustion, that is constant volume heat addition process. And so 2 to 3 was constant volume heat addition process, and 3 to 4 is your isentropic expansion process. So this is your expansion process, or the power stroke, that is when the power is being generated. Here you can see the piston is being pushed from PDC to BDC. So this was the required stroke for our engine, where the work is being generated. So during combustion, the gases burn, that is the fuel burns, and gases are produced, and when the maximum pressure, we were discussing about the maximum pressure over here. So the 3.3 corresponds to maximum pressure, and at this particular point the pressure is acting on the piston, and the piston moves down, generating the power. So that power which is received by the piston is being transmitted through the connecting rod to the crankshaft, and at the end of the crankshaft we are able to get the power at the outside the engine. And the 4 to 1, so this was a confusion point last time which we have discussed earlier. This 4 to 1, so in actual there is no process called as constant volume heat rejection process in actual happening in the engine, but this extra process we have added to the cycle in order to make the open cycle a closed cycle. Now why the cycle has to be made closed? Because open cycles are unable to be analyzed or difficult to be analyzed. Okay, and in order to make them easy for analysis, we want to make it closed. So 1, 2, 3, 4. If the exhaust was supposed to be shown from here, then the line would have, exhaust line would have gone like this, and here it would not have closed. Correct? It would have remaining open. So what we have done, we have added a process over here, imaginary process over here, 4 to 1, which we call as a constant volume heat rejection process, and made the cycle close. So now you can see 1, 2, 3, 4, 1. This becomes your closed cycle. And now since we know that we have discussed, rather you have learned this, what is closed cycle, what is open cycle in thermodynamics, and now you know that 1, 2, 3, 4, 1 is a closed cycle. And whenever you have analyzed, you will be analyzing 1, 2, 3, 4, 1. Now this 0 to 1, which is suction, and 1 to 0, which is exhaust. So 1 to 0 is exhaust. So this two will not be counted from the thermodynamics point of view, because the thermodynamics point of view, 1, 2, 3, 4, 1 will be your cycle, Otto cycle. Okay, so this, though these two processes are there, one is corresponding to suction, where you are inletting the allowing the mixture to flow across the boundary from outside to inside, and 1 to 0 is the process where you are going for exhaust. That is 1 minute. Hey Chanda, आगे दरवाजा उघड की, दरवाजा वाजेल. So 1 to 0 is the process where you are allowing the gases to flow across the boundary, that is from inside to exhaust. Inside to outside. That means fluid is crossing the boundary over here. And whenever you are talking of a closed system, the fluid is not supposed to be cross the boundary. Correct? That is the case where we will be simplifying the process, and we are making it amenable to analysis. Okay, so in order to make it easy for analysis, what we did, we converted an open cycle into a closed cycle by adding one imaginary process 4 to 1. Okay, and this 0 to 1 and 1 to 0 we generally don't show in our theoretical auto cycle. Okay, so that becomes a very important thing what you have to remember. And after understanding this particular PV diagram or auto cycle, then we said in a similar manner we can go for discussion of diesel cycle also. So you can see over here a comparison of auto cycle and diesel cycle. So you can see a similar, the same figure I have put over here. Here you have the suction, you have compression, the heat addition, the expansion, the heat rejection, and the exhaust process. Similarly, here we will have 0 to 1 will be a suction. Okay, and during suction, what happens? The piston moves from TDC to BDC. Okay, so piston moves from TDC to BDC. So the suction is happening. And here, remember, in a diesel cycle, we are not allowing the air fuel mixture, rather we are allowing only air to come into the cylinder. Okay, so the air is sucked into the cylinder in the process 0 to 1. So this corresponds to intake or your suction process. Now 1 to 2 is your compression. Okay, isentropic adiabatic compression. Now what is why this earlier we have not discussed about this adiabatic when we initially discussed. What is this adiabatic? Adiabatic means we are not allowing the heat to cross the boundary, correct? So through the boundary of the system, heat is not allowed to go out. So we ensure that, or we say that whatever heat is being produced, that is going to be retained inside, and that is going to take part in the process. So that is where we are calling it as adiabatic. So ideally we are talking of it to be adiabatic. Practically it will not be adiabatic because the material, whatever material you use for the boundary of the system, there is going to be heat losses. So practically it will not be adiabatic. But here we are assuming that it is adiabatic ideally, and therefore we are saying this is isentropic compression from 1 to 2, adiabatic compression from 1 to 2. So 1 to 2 your compression process. Now you have reached over here similar. So during 1 to 2 process, what happens to piston? Piston moves from bottom dead center to top dead center. So during the top dead center, the piston when the piston reaches the top dead center, now only the clearance volume is remaining. So this is your clearance volume. So now the mixture is accommodated over here to this particular clearance volume. And here in an auto cycle, we said at 2 what happens? At 2 the spark was being given. Spark was being given, correct? So that was leading to the burning of the gases. Now similarly, what is here? Here during suction we have sucked the air. The air has been compressed, and at 2 due to compression, and we know we have already discussed that in diesel cycle the compression ratio is from in the range of 16 to 22. So very high compression ratio. So the due to higher compression ratio, due to the compression, what happens? The volume decreases, and when the volume decreases, the temperature and pressure goes on increasing. Okay, so already the pressure has increased. Correspondingly, temperature will also increase. Now the air is hot enough to such an extent that, so underline the word hot enough to such an extent that at 2 you just inject the fuel in the form of a spray into the combustion chamber, and due to the heat available inside the combustion chamber, the droplets of the fuel which is going in the form inside of the combustion chamber in the form of a spray, they starts burning. Okay, so what we are doing at point 2, we are spraying the fuel. Here the spark was given in auto. In diesel at point 2, what we are doing? We are spraying the fuel, injecting the fuel into the combustion chamber in the form of a spray, in the form of a droplets of proper size. Okay, now what this particular droplets get dispersed into the combustion chamber gas, and we know what is inside the combustion chamber: hot air. So when the droplet is suspended in the hot air, that means every droplet is now available with the heat throughout its circumference. Okay, so the droplet is being covered by hot air from all sides, and therefore heat starts moving into the droplet. Okay, and due to the availability of the heat throughout its circumference to its outer surface, what happens? The droplets get sufficient heat that it starts burning. Okay, so that is what is the difference where we compare. Okay, at 2 here we are given spark, and due to spark the mixture was burning. Here we have injected the fuel, and the fuel is going into the combustion chamber in the form of a droplets, and droplets are picking the heat, and this particular droplets, when pick the heat, they start burning, and this particular burning we call as auto ignition. Because what is auto ignition? The auto ignition is burning on its own self. Okay, so you might have sometimes tried to burn the paper with the help of sunlight, with the help of a lens, isn't it? So when you concentrate the sunlight on the paper, at a certain point, initially the paper starts changing its color from white to brownish, and at a certain point it starts burning. Okay, that is its auto ignition temperature. It starts burning. So similarly, initially the droplets are going in the form of a fuel, liquid fuel droplets, but at a certain point they becomes hot enough and they starts burning. Okay, so here we are saying that the combustion is happening. Okay, so similarly here in Otto cycle, the combustion we assume to be constant volume heat addition process, but here it is constant pressure heat addition process. Okay, so here we are assuming that the pressure is remaining constant. Pressure is remaining constant when we add the heat in the cycle. Okay, so that is the difference over here. So here we assume that the pressure is going to be remain constant when we add the heat in the system. Okay, so when we add the heat, then since the pressure is remaining, now can we make the pressure to remain constant and the combustion to happen uh, without moving the piston? Obviously no. So because we know that due to combustion, the fuel which is in the form of liquid droplets is going to burn and form the gaseous that is byproducts. Okay, so this particular gaseous byproducts, they are accommodated in the volume, and since the volume is constricted, now the pressure increases, but we want to maintain the pressure constant. So what we have to do? We have to move the piston from TDC to BDC towards BDC. So you can see from here to here, the piston is being moved. Here we assumed that everything was happening instantaneously. Instantaneously. Remember the word instantaneously. Without no time. That is, with no time or negligible amount of time, all the combustion was happening and heat was added into the gases. That is what we are assuming. Here what is the condition? Here we are assuming that the heat is being added at constant pressure. So this is your pressure line. Okay, so your pressure is remaining constant, or this particular whatever value is there, that is going to be remain constant. How it is made able to remain constant? By allowing the piston to move down. Now, by allowing, that is, whatever the pressure is being increased, that is being nullified by increasing the volume. Okay, so during combustion process over here, the volume changes from 0.2 to 3, while here the volume was remaining constant. Here the pressure was increasing, here the pressure is remaining constant, and therefore the diesel cycle is also called as a constant pressure cycle, and Otto cycle is also called as a constant volume cycle. Okay, so this is a constant volume heat addition process, this is a constant pressure heat addition process, and now at 3 you can see the pressure is again similar to the 2. So peak pressure at 2 or 3 is same. Here the peak pressure was at 3. Here you can take it as at 2 or 3 because we are assuming that at 2 and 3 the pressure is remaining constant. Correct? Okay. Now after 3, your isentropic expansion process starts. Okay. So the expansion is going to happen. So similar to this, here also expansion is happening and it reaches 4.4. So we have here isentropic expansion process. So during expansion, what is happening? Piston is moving from TDC to BDC. So already it has started its motion during combustion process from 2 to 3, and from 3 onwards, we say up to 4, the piston is moving further towards BDC and it reaches BDC at 0.4. Now again, similar to 4-1 process, here also we have a 4-1 process, but in actual again there is no such process happening inside the combustion chamber, which is again a imaginary process. So 4-1 is a constant volume heat rejection process. See, nothing is happening over there, just it is an imaginary process. Okay, so it is, we are assuming that it is a heat. Why we are adding this imaginary process? Because we know that this is an open cycle now and it has to be made close, and in order to make it close, what we require? This particular vertical line, and vertical line can be achieved by assuming that it is a constant volume process. Correct? So we are putting a constant volume imaginary process from 4 to 1, which makes this particular open cycle into a closed cycle, and then from 1 to 0 there is an exhaust. Okay, so that is how we have here the diesel cycle, where we have calling it as a constant pressure cycle. So similar to what we have here, constant volume, here we have a constant pressure cycle. Okay, so once again 0 to 1 was a suction. So during suction the piston was moving from TDC to BDC. Then 1 to 2 was your piston moving from TDC to BDC, sorry, BDC to TDC, that is bottom dead center to top dead center, and at point 2 the piston reaches top dead center. Top dead center. Now the compression is maximum. It has been done. So whatever compression was supposed to be done is being done, and now all the air is being accommodated in the clearance volume. And at this particular hot air, what we are doing at point 2, at point we are spraying the fuel in the form of droplets, and this particular droplets, which are of a proper size, remember the word size, proper size is very important. Proper size goes into the combustion chamber, it gets dispersed into the combustion chamber, and as they are suspended in the air, hot air over there in the combustion chamber, every droplet is able to get the heat from the surrounding air, and when sufficient amount of heat is able to be absorbed, we assume it is going to auto ignite. Now you can understand that why we are considered here, it was considered as instantaneous, but here we are not considering as instantaneous. Why we are not considering instantaneous? Because we know that now at point 2 we are starting the injection. Now when we inject, the flow of fuel coming through the injector is initially broken up into droplets. The droplets has to go into the combustion chamber. There it has to get dispersed into the combustion chamber. Further, it has to pick up the heat from the air. Then it has to increase its own temperature. And finally, when it reaches self-ignition temperature, it will burn. So, and all this is going to take a time, some amount of time, which is not the case here. Because here what was there? Earlier mixture was there and it was already hot. Why it was hot? Because we have already completed the compression process. So hot mixture was there, only some ignition source was required. So just we have given the ignition and suddenly everything is burning. That is the assumption. Okay. But here it is not the case, because only what is there inside the combustion chamber is only air, and air itself cannot burn. Correct? And therefore we are injecting the fuel. Now the fuel coming out of the injector, the flow is being broken, and it is being converted into droplets. Droplets has to get dispersed into the combustion chamber, throughout the combustion chamber, spread into throughout the combustion chamber. Then they have to pick up the heat. Then they have to reach a self-ignition temperature and burn, and this will require some amount of time. And to give that much amount of time, we have given some motion of the piston corresponding to 2 to 3 process, during which we are now able to move the pistons from 2 to 3, that is top dead center from here to here almost. We are making the piston to move. Why? We want to maintain the pressure constant. Okay. So whatever the combustion goes on happening, and we know that the pressure is tending to increase, but we are not allowing it to increase. But by increasing the volume, we are balancing it out and ensuring that the pressure is going to remain constant. And therefore, we call this particular cycle as a constant pressure cycle. So 2 to 3, pressure remains constant, and at 3 we say the combustion is complete. Heat addition process is complete. Constant pressure heat addition process is complete. And further, as the piston moves from 3 towards BDC, volume is going to decrease, and when the volume is decreasing, the pressure is tending to decrease. Okay, so the pressure is coming down from 3 to 4, and when the piston reaches bottom dead center, the pressure is now corresponding to 0.4 P4, this much. So from here to here, the pressure has decreased. Okay, and further we imagine a process. We have added an imaginary process, which is constant volume heat rejection process, 4 to 1. Now 4 to 1 is constant volume heat rejection process, and therefore the pressure we say is due to here heat decrease. So since the heat is decreasing, the pressure will come down. Okay, so the pressure decreases from P4 to P1, and at a particular 1, which is corresponding to atmospheric pressure. So this is your atmospheric pressure, correct? So at atmospheric pressure, we are pushing the gases. We are opening the valve. So here we open the valve, the exhaust valve, and we push the gases out through the exhaust manifold. Okay, till all the gases are removed. Okay, and correspondingly the piston is moving from BDC to BDC. So out of the 4 strokes, initially first stroke, when the piston was moving from top dead center to bottom dead center, it is utilized for suction. And the last one, that is when the BDC, from BDC to TDC, the piston was moving, which is going for suction and exhaust. And in the remaining 2 strokes, this particular cycle is happening. So the second stroke was from BDC to TDC, where the compression was happening. Then the third stroke, that is the piston moving from TDC to BDC, 2 things are happening. The combustion is happening and expansion is happening. Okay, and when the piston is at BDC, the 4th imaginary process is assumed to be happen, and the 4th stroke is your exhaust stroke. So first stroke suction, second stroke compression, third stroke combustion and expansion, and this is happening when the piston is at bottom dead center, and the last stroke 1 to 0 we have exhaust. So this is your diesel cycle. So I hope you might have completed written the answer of the question the way we have written the Otto cycle as homework, which I have given in the earlier class. So which was the first question of your assignment number 1. Okay, so that I think everybody has understood. Now anybody who has not understood can open their that is unmute themselves and can ask any doubt with respect to Otto cycle or diesel cycle. Anybody having any doubt, let me know. Anybody having any doubt, please let me know. Or should I assume that everybody has understood?
Yes, sir.
Okay. Okay, okay. So, assuming that everybody has understood, now I think since I explained in the last lecture and this lecture also, I assume that everybody has understood the auto cycle as well as diesel cycle, and hope you will complete the question number one of your assignment. Okay. So moving ahead, now once we have understood the auto cycle and diesel cycle, um, okay. Now moving ahead. Uh, we will be moving towards the wall timing diagram. So earlier in the lecture itself, we were saying that we will be discussing about the timing diagram. Uh, Somebody's audio is not muted. Please mute it. Okay. So we are now discussing about the timing diagram. Now, what is this timing diagram? So timing diagram is it's a graphical representation of when the walls are going to be opened or closed. Now, when it is for a four-stroke engine, obviously we know it is there are walls, and therefore it will be called as wall timing diagram. And when this is for a two-stroke engine, there are no walls. Instead, we have ports over there, and therefore we call it as a port timing diagram. So remember this. So the timing diagram for an engine is the graphical representation of when the walls oblique ports are being opened or closed throughout its cycle. And we know that in a four-stroke cycle, four strokes are going to be there for completion of one cycle. Now, the four strokes we have displayed over here in a graphical manner. Okay. So let us this. Basically, this is theoretical wall timing diagram. Now, remember again, we have a theoretical wall timing diagram over here. So, a theoretical wall timing diagram, basically, as the word theoretical is there, it is not practical. Okay. So, practical, it will be something different. So, here we are talking of only theoretical. So, now we'll go back over here. Now see here, when we were discussing at zero, in order to suction to happen, the wall, which wall is supposed to be opened over here? The inlet wall, correct? So the inlet wall was supposed to open over here. Now at the end of when the piston reaches BDC, the suction is going to end. And if you want to end the suction, you have to close the inlet wall over here, correct? So once the inlet wall is closed, in the that is in the first stroke, when the starting of the first stroke, inlet wall is open, and the end of the first stroke, the inlet wall is closed. Okay, already the exhaust wall is still closed. Now both the walls are remaining closed, and we have here the mixture entrapped between the cylinder piston arrangement, and your compression is going to happen, compression is going to happen, expansion is going to happen, rejection, heat rejection is going to happen. And when it comes to 1.1 back, that is 0, 1, 2, 3, 4, 1, at this particular point 1, we are again supposed to open the exhaust wall. Why? In the next process is exhaust. So here we will be opening the exhaust wall, and when it reaches the top dead center, we are supposed to close the exhaust wall. So this we are talking theoretically. So the same thing when we put it on the graphical representation manner, then it is what we call as a timing diagram. So let us start initially. So as we discussed in the first stroke, initially consider that both the walls are closed. Okay. Now, if you want to have the first stroke, which is suction, then in order to suction to happen, we have to open the inlet wall. So inlet wall is opened. Here the inlet wall is open at top dead center. So this is the point indicating top dead center. This is the point indicating bottom dead center. So this is a top dead center. This is bottom dead center. So at top dead center, the inlet wall is open. Now the piston is moving down from top dead center, and the suction is happening. Okay. So the suction will continue till the piston reaches bottom dead center. Okay. So from top dead center to bottom dead center, the suction was happening. Suction was happening, or suction is happening. Why? Because the inlet wall is open. Now we want to stop the suction. So what we did? Inlet wall is closed. Inlet wall closed. IVC. Here it was written IVO. IVO corresponds to inlet wall opens. So here inlet wall was open. Here inlet wall was closed. Wall was closed. So this is your closing. Now already the exhaust wall is closed. Now we have closed the inlet wall also. So both the walls remaining closed. Now we have compression. So the piston is moving from BDC to TDC. We are denoted by this line. Okay. Piston is moving from TDC to BDC. So compression is indicated by this particular line, and until from here to here, that is piston moving from BDC to TDC, the compression is happening. So when the piston reaches top dead center, the compression is going to end. So here, at this particular point, IVO, initially we started with 0 point. Okay, this was the point 1, and from 1 to 2 we had compression. So the compression was happening from 1 to 2. So here at point 2 the compression ended, and we can see over here ignition is going to be there, spark is going to ignite. Okay, so this is a point at the top dead center. At point 2 we say we are giving the spark theoretically, correct? So the spark is given over here, so we are denoted by ignition. Okay, so at the top dead center, that is at the, we generally say, what we say generally at the end of the compression stroke, the spark is given. Okay, so at the end of the compression stroke, the spark is given, that is ignition is happening. Now why this word ignition is coming? The ignition is the process whereby we ignite the mixture, we burn the mixture, okay, with the help of a system which we call as a ignition system. Okay, so that is where the ignition word is coming. Till now we were just using the word burning or giving spark. So the spark word is coming from the process of giving the spark in order to burn. Okay, so the spark was happening or ignition is happening one and the same. So it is ignition over here. So at point 2 we have ignited it. Still all the both the walls are remaining closed, and your here combustion starts. Okay, so in a 2-stroke engine, in a 4-stroke SI engine, we assume that the ignition is going to happen, and it is going to be instantaneously at point 2. So the piston is not moving. So all the combustion is going to happen over here only, and thereafter your expansion is going to happen. Okay, so expansion is going to happen. So during expansion, what happens? Piston moves from top dead center to bottom dead center. So as it moves from the top dead center to bottom dead center, why this particular this motion is happening? Because the gases inside the combustion chamber are pushing the piston down from TDC to BDC. That means piston is receiving the energy, and that particular energy through connecting rod, it is transmitted to the crankshaft, and the crankshaft is going to rotate. Okay, so now the piston reaches BDC, and at BDC we know still both the walls are closed. Both the walls are closed. But next stroke, so from here 2 to 3 we have reached. Sorry, 2 to 3 here. It was 2 to 3 here because combustion was happening at a constant volume. So 2 and 3 points are here, and 3 to 4 we have reached over here. Again, we are assuming here one more 3 to 4. 4 to 1, which is a constant volume heat rejection process happening over here, and 1 to 0. 1 to 0 is again 1 to 0 is this exhaust. So during 1 to 0, the piston was moving from bottom dead center to top dead center, and in order to exhaust to happen, we have to open the exhaust valve. So EVO exhaust valve is opened over here, and as the piston is moving from BDC to TDC, the gases are pushed out through the exhaust manifold. Okay, and at the end of the exhaust stroke, you are going to close the exhaust valve. So exhaust valve closed. EVC, exhaust valve is closed. exhaust valve is closed. Okay, so this is how a cycle is being completed. Okay, so initially suction, the compression, the expansion, and the exhaust. So these are the four processes happening corresponding to four stroke. And in between here was the combustion, which was a constant volume heat addition, and here was the constant volume heat rejection process. Okay, they are not coming into picture because correspondingly at that particular processes, nothing is happening with respect to piston. Okay, piston is stationary. So here it will be denoted by a single point. Okay, so whenever it is stationary at the TDC or BDC, the constant volume heat addition and constant volume heat rejection processes are happening. So it will not be coming over here. So the remaining initially we have suction, compression, expansion or power, and we have exhaust. Okay, so these are the four things happening corresponding to the four strokes of the piston, and correspondingly now we have understood when the valves are being opened and closed and when the ignition or the spark is going to happen in case of a four stroke engine timing diagram. And since the valve are opened and closed is being denoted on the diagram, then we call it as a valve timing diagram for a four stroke engine, which is theoretical. So this is very important. So underline the word theoretical. This is a theoretical valve timing diagram. Theoretically, it should happen like this, but not necessarily the practical. It may happen like this. Okay. So theoretically, now we have here suction, compression, expansion, and exhaust happening. Correspondingly, we have this particular theoretical valve timing diagram. Now, this is your actual valve timing diagram. Now, before going for actual valve timing diagram, basically we have to understand why there is a difference between theoretical and actual valve timing diagram. Now, earlier in our earlier cycles, we have discussed about. So let me check out if that PPT is with me. So if it is there, we'll be able to understand properly. So 1 minute. Okay, so this is the arrangement where we operate the valves, correct? Now, here you can see in the theoretical diagram, we are assuming that we are opening and closing the valves at dead centers, either top dead center or close bottom dead center. Okay, so either opening or closing, it is generally done in a dead center, and which means again it is instantaneous. But you can see over here, this is a mechanical operation, and the mechanical operation cannot be done instantaneously because it has some inertia. So, so if there's an inertia and if you are applying a force, remember, if you are applying a force, we have to slowly go on increasing the force, and then it will start moving. And until it moves, it will be again consuming some amount of time. That means there will be some amount of time required due to its inertia. First thing. Second thing is, see, if you let us move some. Okay, here, if you see this particular, let me check out another. Okay, so these are the cam lobes. Okay, these are the cam lobes which are going to make the valves move. Now you can see over here, this is a cam lobe. This is called as a cam lobe. This is a cam shaft. Now here there is this is up to somewhere here. This is having the same diameter, but here the diameter is going to increase and it will become maximum over here. So here it is clearly visible. Okay, so you can see from here to here it is increasing. Here from here to here it is increasing, and then it is going to decrease. So this is the region where it is going to lift. Since the diameter is increasing, the follower, this is called as a cam and this is called as a follower. So the follower is going to be lifted up. That means there is the inertia of the follower coming into picture, correct? So the follower, if it is supposed to be pulled, then the inertia has to be taken care, and that due to that particular inertia, what happens is we cannot make it suddenly move. So we have to slowly. That means it will consume some amount of time. Moreover, suppose that means what is the shape of the cam? The cam is something like here. It will be initially half of the part. It is, let us assume that it is circular, and then it will be like this. Okay. So, and this is the portion is called as a cam lobe. So this particular cam lobe. So this portion I am showing. So this particular cam lobe like this is going to push the this particular follower up. Now, in order to make this to happen, we have to ensure that the cam lobe is designed in a proper manner. So, if you suddenly want to make it move from up to down or down to up, then the cam lobe shape cannot be like this. So, initially it will be like this, circular. There will not be any motion. Okay, if the cam lobe is circular, there will nothing motion will be there. So, we are giving an extension over here. So, this particular extension, if I want to have a sudden movement, then up to here, and then suddenly the cam lobe has to be here like this, which is not possible. And if that is done, then working is very difficult. And therefore, that means if you see the cam lobe over here, the cam lobe has to be then here, this same diameter over, and then suddenly wherever it is increasing, instead of that, up to here it will be same diameter, and suddenly it has to increase like this. That means follower will come over here and suddenly it has to move up, or from this side if it is coming, suddenly it will move down. So there will be a sharp decrease over here, which is not a possible thing. Okay, and therefore, this arrangement is not possible. If that was supposed to be like that, then the arrangement has to be made like that, which is not possible. And therefore, we say some dynamic process and some design parameters are coming into picture, due to which we cannot, underlining the word, we cannot instantaneously open or close the walls instantaneously at dead centers. Once again, we cannot open or close the walls instantaneously at dead centers. Okay, so but theoretically we want like that. Theoretically, what we want the inlet wall to open here, we want the inlet wall to close here, we want exhaust wall to open here, and we want exhaust wall to close here. So then what has to be done? Because instantaneously it is not going to happen. It is going to take some amount of time to open and to close. Now we want the suction to happen from top dead center to bottom dead center. We want the wall to remain open. So if you want to remain the wall open at top dead center, then you have to start its opening somewhere here before the top dead center. So when you start the opening from here somewhere before the top dead center, so if you put in terms of degrees, some 10 to 20 degrees before top dead center, by coming over here it will be completely open. Now you want to remain open over here, so you will be starting the closing over here, and it will close sometimes after bottom dead center, that is some degrees after bottom dead center, 10 to 20 degrees after bottom dead center. So now your opening point will become some 10 to 20 degrees before top dead center, and your closing point becomes 10 to 20 degree after bottom dead center. So opening becomes 10 to 20 degree before top dead center, and closing point becomes 10 to 20 degree after bottom dead center. This is for inlet wall. Similarly, we want the exhaust valve to remain open over here, and till here, top dead center, we want it to remain open. Now, if you want to completely open over here, we have to start it opening somewhere before top bottom dead center. So some 10 to 20 degree before, we have to start it opening so that it will be completely open at bottom dead center. It will remain open throughout. The exhaust is happening, and from here we can start closing, and some 10 to 20 degree after top dead center it will close. So the exhaust valve is going to open some degrees, 10 to 20 degrees before bottom dead center, and close 10 to 20 degrees after top dead center. Okay, so this is the practical thing. So practically, when we are talking of the all timing, it will not be the way what has been represented over here. Rather, it will be something like this. So here, what is shown is, you can see over here, the inlet valve is opened over here. Okay, so since it is opened over here, so it will start opening over here, and by the time it reaches over here, it will be completely opened. Completely opened. Okay, now it will start its suction, and suction will go on, and we want it to remain completely open till bottom dead center. Because see, why? If we have started the closing from here and we have completed this point, if it was here, then and suppose we have started the opening over here, it will be completely opening somewhere here. And if you have started the closing from here and it was completely closed over here, then the effective suction was decreasing. That means your volumetric efficiency is going to be compromised. What is volumetric efficiency? The efficiency with we are filling the combustion chamber. That means to how much extent we are able to fill. Already the engine is running at 2000, 4000, 5000 RPM rotations per minute. And every cycle has only 1/4 of it available for suction, filling the combustion chamber. And if that too is being compromised, up from here to here it will be available, and from here and to here it is partially available, that means we are unable to fill the combustion chamber with sufficient amount of mixture or air. Correspondingly, if it is a 4-stroke or a 2-stroke engine, SI or CI engine. It's not a 2-stroke and 4-stroke, it is SI or CI engine. So that means our filling capacity will be decreased. So in order to ensure that your filling is to the maximum extent, why we want to fill it maximum? Because in the available circumstances we want to produce more work. So if whatever the available volume is there, we will be trying to fill it to the maximum, so that in the available we will be accommodating more air fuel mixture and more power can be produced. So we want to ensure always that volumetric efficiency is going to be higher. What is volumetric efficiency? The efficiency of filling the volume. This is what we call as volumetric efficiency. So by how much efficiently you are filling the volume. So if you are able to fill it 100% volume, that is, suppose the volume is 1 liter and you are able to fill 1 liter mixture in it, then your efficiency is 100%. Okay, so generally it is assumed to be more than 90% volumetric efficiency in case of engines. Okay, in supercharged engines it may be sometimes above 100% also. We will be discussing in this in the chapter number 4. Okay, so let us come back. So now, in order to maintain the volumetric efficiency, we want to ensure that inlet valve is completely opened at TDC and inlet valve is completely remaining open till BDC. And in order to ensure this, we have to open it before TDC and we have to close it after BDC. So your inlet valve is closed over here some degrees, and it is shown here 20 degrees, and we are going to close it somewhere 35 degrees after BDC. Now here one more thing we have to understand. Being a mechanical engineers, we know that when the fluid is flowing, suddenly fluid cannot flow. Suddenly, suppose you open the valve, suddenly fluid will not flow. Initially it will slowly start moving, and then its velocity will go on increasing. Why? there is something called as inertia. What is inertia? Inertia is a tendency to keep a stationary body in a stationary condition or moving body in a moving condition. So when the wall was closed, the charge in that region was stationary. It was not moving. You suddenly open the wall. Suddenly open the wall. Obviously, there is some pressure difference. And due to the pressure difference, there is a tendency that the fluid may move from higher pressure region to lower pressure region. That is from outside to inside when the inlet wall is opened. But inertia coming to picture. What is inertia? Inertia is a tendency to keep a stationary thing in a stationary condition. So due to inertia, there will be resistance for motion of the gas. And as and when the inertia is overcome, the gases will start moving. That means even though you are completely opening here, you are not able to, that is whenever you are opening, suddenly you cannot assume that it is going to flow. Initially, some amount of time will be required to overcome the inertia of the gases. Till now, we were discussing about the inertia of the parts. Which parts? Cam follower, etc., etc. The wall, etc. So all the mechanical components will have some inertia. But the flowing fluid also will have inertia, and that is again another reason why we have to open it early. So when you start over here, by the time it reaches over here, it will overcome the inertia, and we will ensure that when the piston reaches TDC, the wall is completely open and the fluid will start in its maximum capacity through the inlet manifold across the inlet wall, and it will continue to flow till the piston reaches PDC and inlet wall is still completely open, and slowly we will try to close it, and the closing will happen at inlet wall closing point, which is 35° after BDC. So inlet wall opened over here 20° before TDC, and inlet wall closed 35° after BDC. Before, here it was before and here it is after. So now your net total suction stroke, which was theoretically 90 degrees from TDC to BDC, is now here 20 plus 35, around 55° extra. That is 90 plus 55 is your net suction stroke now in terms of crank angles, which was theoretically 90°. Now it has increased from 90 plus 55. So 20° here it has increased, and 35° here we have increased. Why this has to do? You have to overcome the inertia of the different parts. You have to overcome the inertia of the flow, etc., etc. And to ensure that volumetric efficiency is going to be maximum, so that we can fill the mixture to a maximum amount, so that more power can be produced as far as possible. Okay, now theoretically we said that here the inlet wall is going to close, and since both the walls are going to remain closed, and so here we said both the walls are here remain closed, and therefore the mixture is trapped and the compression is going to happen. But here you can see, since this wall is opening up to over here, then after this particular point already the exhaust wall is closed, but here the inlet wall is closed. So that means your compression will start here instead of at BDC, it will start here. Okay, so suction was from here to here, and from here your compression is going to start. So this is your compression, this is your compression, this is your compression. So as the compression is proceeding, so during compression what happens? Piston moves from BDC to TDC. So the piston is moving from BDC to TDC, and at this particular location your inlet wall is also closed. Now the mixture is being trapped, and since the piston is moving up, it is going to get compressed. So the compression starts, and the compression continues till TDC, till TDC. Okay, so the compression is happening from here, it is going to happen till TDC. Okay, but now again there is some change over here. This particular ignition, whatever we have discussed, theoretically it was at point 2, that is TDC. But in actual, the ignition is happening some degrees before TDC. Why? Again, we have discussed when we were discussing about the Otto cycle, we have said that we are assuming that combustion is going to happen instantaneously. But do you feel that the burning process will happen instantaneously? Obviously not. Okay, so the burning process will not happen. So you have seen many times burning a log of wood in a chula. Will it suddenly completely log will burn completely? Obviously no, it will not burn. Okay, so it will take some amount of initially it will start burning. So here we have given a spark. So that spark has to reach all corners of the combustion chamber. Heat has to reach all corner of the combustion chamber to make it burn, and the heat transfer has to happen. So slowly the mixture in the inside the gas is going to burn from the point of the spark towards all sides. So the flame is going to propagate. Okay, and this will require some amount of time. But what we want is we want the maximum pressure to be applied on the piston when the piston is at TDC, because we want to push it down. So what we do for that is we start, instead of starting the ignition over here, we give the ignition spark over here. Now by the time it moves, piston moves from this particular point to TDC, the flame, due to spark, the mixture nearby the spark will get ignited, and the flame is going to propagate throughout the combustion chamber, burning all the mixture. And by the time the piston reaches TDC, all the flame inside all the mixture inside the combustion chamber is being burned, and the maximum pressure is being produced. So point 3 is reached. So point 3 is reached over here. So now this becomes the point 2 over here, because not point 2, it is a spark point. So point 2 is still the same, but the ignition point is moved towards, that is we have taken it early. So ignition is given early, that is theoretically we say at the end of the compression stroke we ignite the mixture. But here see, we are not igniting the mixture at the end, before it reaches the ending, that is before the compression is going to end, we are igniting the mixture, and we are giving this much time for ignition to happen, combustion to happen, burning to happen. Okay, because we want all the mixture to burn and produce sufficient pressure to push the piston down. So by the time the piston reaches stop dead center, all the mixture has been burned, and the burned mixture with a maximum pressure starts pushing the piston down from TDC at this particular point. And for that, ignition has been made early by 35 degrees. So this can be depending on different designs, the angle, this particular angle is going to change. So all these angles are going to change from design to design. Okay, so in this particular figure it is shown 35 degrees. So some 35 degrees before the TDC, the spark is given, and the combustion will happen here, and it will be completed, and the maximum pressure is going to be applied on the piston crown by the time the piston reaches TDC, and it will be pushed down. So when the piston is pushed down, we call it as power stroke or expansion stroke. So expansion starts over here. So the compression was from here to here. Even though see, theoretically it was from here to here, 90 degree, completely 90 degree. But here you can see it has been reduced by 35 degrees. Okay, so 90 minus 35 is your effective compression stroke in this particular case. Okay, so from here to here is your effective compression. Now in this particular effective compression, again some 35 degree, the burning is also contributing. So mixture was being compressed and heated up due to compression from this point to this point. Further from here to here, still heating up due to compression is there. In addition to that, heating due to combustion is also there. Okay, so from this point to this point, that is this 35 degrees, heating is happening due to both the reason. Which both reason? It is heating is happening due to compression because the piston is moving from towards TDC, and also due to combustion. That is the liquid fuel vapor is going to be get converted into gaseous combustion products, and therefore the pressure is going to increase. So the pressure is increasing in this particular 35-degree due to both the reasons, and by the time it reaches top dead center, the pressure becomes maximum. And since the pressure is maximum over here, and now the piston has reached the top dead center, it can move down and it will receive the piston. Now, this 35-degree is going to play a very important role. If you make this more early, then what will happen is the combustion will start over here, and the piston is trying to move upward, and they are due to combustion there will be increase in the pressure, and it will try to stop the motion of the piston, which is being moved towards the upward side. So it will try to resist the motion. So it is very important, it is very critical to decide when the ignition should start. Okay, so that is again a very important point. So accordingly, whenever you give the ignition at a different points, your combustion is going to change. Okay, so the combustion is going to happen at a different points when you are it will become late or early, and accordingly we will say the ignition is advanced or retarded. Okay, it will we say so. Earlier we make, we call it as advanced. The late we make, we call it as a retarded. So the ignition advance is that this is the point where what we call as ignition advance. Okay, so early we make, we call it as advanced, and late we make, we call it as retarding. So theoretically some point will be finalizing, and if you make it early than that, we say it is ignition is advanced. If you make late than that, then we call it as retarded. So ignition advance and retarding with the help of a spark. So when we give the spark is very important over here, and this particular spark happening over here is what is resulting in the combustion. So the combustion process, we can assume that it is completed over here, and from here the expansion is going to happen. So the expansion is going to happen, and the expansion will continue. So the generally theoretically the expansion was happening from TDC to BDC. So the piston was moving from TDC to BDC, and your expansion was supposed to happen. Okay. Now, obviously, during the expansion, again, both the walls are supposed to remain closed, and therefore, already both the walls are here also in the compression, both the walls were remaining closed. Here during expansion also, both the walls are remaining closed. And theoretically, at the end of the expansion stroke, we are going to open the exhaust wall over here. Okay, exhaust wall is opening at BDC theoretically, but practically you can see we want to completely open over here, and in order to open the wall completely over here, we have to start the opening early, and some 35 degrees early we have started the opening of the wall, exhaust wall. So now your effective expansion stroke will become from TDC to this, that is 90 minus this 35. This will be your effective expansion stroke. Effective compression stroke was this 90 minus this 35, that is this point to TDC, and effective expansion stroke is from TDC to this particular point, that is when the exhaust valve opens. Okay, so this is your expansion stroke or power stroke. Now here we open the exhaust valve, and since we have opened the exhaust valve, exhaust will start. So this is the exhaust process starts from this particular point. Theoretically it was supposed to start from here, but actually it is starting from here. And this exhaust valve, we want to remain it open till TDC. So here we start closing of the valve, and here we close the valve actually completely. So here is the point where we have closed the exhaust valve, which is at around 10 degrees after top dead center. So Now your net exhaust stroke is this 90 plus this 10 plus this 35. That is 90 plus 45 is your net exhaust stroke. Okay, so net exhaust stroke is your 90 plus 45. That is from this point to this point. So now the cycle has been completed. Okay, 4 strokes has been completed. That is suction, compression, expansion, and exhaust. All the things has been completed. Okay, and on this particular curve, now we have denoted when the particular walls are going to open or close, and therefore this is called as the wall timing diagram. Sorry, walls are going to open and close, and therefore this is called as wall timing diagram. So inlet wall open here, inlet wall close here, exhaust wall open here, and exhaust wall closed here. Okay, and the spark was given here. So this particular 5 points are very important, and this particular angles depend on what is the speed of the engine. Very, very, very important, because see, when the engine is moving slowly, the piston is moving slowly. Suppose the speed of the engine is 500 rpm. Now when the suppose the 600 rpm, that means in 1 minute we are going to have 600 motions. Okay, so 600 revolutions. Somebody want to get in? Okay. Okay, so that means we were discussing about the speed. Now when we have a slow speed engine and a high speed engine, which means see, for opening and closing the valve, the amount of time required will be less or more, or it is constant. It is going to be constant, isn't it? It is not dependent on what is the rotational speed of the engine. So as the speed of the engine becomes lesser and lesser, small amount of this will be only required for opening or closing. That means these angles are going to change as the speed of the engine is going to change. That is what I'm making the point over here. So this angles is a function of the speed of the engine. So as what it means is that, see, as the speed of the engine increases, the time in which the piston is going to move from TDC to BDC becomes less. That means the slower the engine, the same piston moving from TDC to BDC will be requiring more amount of time. While as the speed increases, the same piston moving from TDC to BDC will have small amount of time. And in that particular small amount of time, how much time we are going to give it to opening and closing. Okay, so depending on this particular time, since the slow engines the time is more, whatever time is available for opening and closing remaining constant, that means a small angle is sufficient for opening and closing when the speed is lesser. So when the speed of the engine is lesser, the value of this particular angles are going to be smaller. And when the speed of the engine is higher, the value of this particular angles are going to be more. So depending on that, what it means is that depending on the speed of the engine, the value of this particular angle goes on changing. So that is where I said that what degree we want to give ignition spark, it depends on the engine speed. So if the engine is operated at a lesser speed, then the ignition has to be retarded. If the engine is going to be speeded up, then the ignition has to be advanced. So advanced means make it early, and retard means make it late. Okay, so this particular point we have to take into consideration. So similarly, it will happen with the exhaust and wall opening and closing. So that is where during the design of this particular system itself, we have to take into consideration at what speed we are going to operate that particular engine. Because depending on the speed of the engine, we have to ensure when the valve is going to open and close, and depending on that opening and closing, we have to define this particular angle, and depending on this particular angle, we have to design the cam lobes of the cam, which is going to operate the valves. So the the design of the cam lobes of the cam, which is used for the opening and closing of this particular walls, depends on what is the speed of the engine, which that is going to be affected, correct? And therefore, before operating the engine, we have to decide at what speed we want to operate. So theoretically, there will be some speed decided for optimum operation. So we will say this engine is supposed to be run at 1000 rpm. This engine is supposed to be run at 2000 rpm. So at that particular conditions, it will be optimum. So the conditions are optimum and it will give you the maximum power. Okay, so such things are going to be there, and accordingly, what the point we are discussing over here is this values of this particular angles are going to increase and decrease depending on the speed of the engine. So lesser the speed of the engine, lesser will be the values of this particular angles. So first value is corresponding to the inlet wall opening. So this can be 15 or 10, which is shown over here 20. So this particular values, whatever has been denoted over here, are generally for high speed engines. Okay, so for a low speed engine, this may become 10 or 15. Here similarly, the inlet wall closing, which is 35 over here, may become 20 or 25, depending on the speed. So when the lesser the speed, the angle will become more or more lesser. Similarly, the exhaust wall opening over here, which is 35, may become 25 or 30 with a lesser speed. And here, this may also become 7 or so. Okay, so all this angle, the value of this particular angles are going to decrease when the speed is decreasing, and value of this particular angles are going to increase when the speed is going to increase. So in the examination, you may be asked to draw wall timing diagram for a slow speed engine and a high speed engine. Okay, it may be asked for a slow speed engine and a high speed engine. Then you should be in a position to tell right there the values of this particular angles. Okay, so check out the books for the exact value of the angles of for a slow speed engine and for a high speed engine. Okay, hoping to understand, hope you have understood the wall timing diagram for a 4-stroke engine. Once again, I will revise it, and then I will go for clearing the doubts. Okay, so initially we have this, what we call as a theoretical wall timing diagram. Here, top dead center, the piston is going to move down. So this is your corresponding suction stroke. During suction, the inlet wall is opened here, the inlet wall is closed over here. Okay, so this corresponds to suction stroke, which is 90 degree. Second, this is your compression stroke, again 90 degree of the crank rotation. Okay, here the inlet wall closes and exhaust wall is already closed, and here you are going to have the compression to happen. At the end of the compression stroke at TDC, the spark is being given, and at this particular point, since spark is given, the combustion is also happening at instantaneously here itself. And since the combustion has happened, the pressure is acted on the piston, and the piston is going to move down. Therefore, the expansion stroke starts over here. So this 90 degree was corresponding to compression, and the next 90 degrees corresponding to expansion. So expansion is from TDC to VDC. Okay, and here at this particular point, exhaust wall is open at VDC, and your exhaust stroke starts. So the exhaust stroke is again the 90 degree from here to here, where when it reaches over here, the exhaust wall is closed. Okay, so here the initial, the suction, then the compression, then the expansion, and then the exhaust. Every process was getting exact 90 degree crank angle rotation, which is theoretical, and the opening and the closing of the walls was happening at dead centers. Opening and closing of the walls was happening at dead center, along with ignition also happening at top dead center. But actually, it is not so. Actually, in order to ensure that walls are opened, completely open, or remaining open till the next dead center, we have to open the wall before dead center and close the wall after dead center. So opening has to be before, and closing has to be after. So here the wall is open, inlet wall is open, here the inlet wall is closed, and instead of 90 degree, it becomes 90 plus 20 plus 35. That is 90 plus 55 is your total crank angle rotation corresponding to a suction. And the compression starts over here. So instead of completely 90 degree, it is 90 minus this particular 35 is your compression stroke from here to top dead center. And ignition was supposed to be happen over here, but you can see the ignition is happening before top dead center some 35 degrees. And here this is there we have assumed that combustion is instantaneous, but here the combustion is over this particular range corresponding to 35 degrees. Now from here your expansion stroke starts and the expansion stroke goes on here. So theoretically it was supposed to be from TDC to BDC, but actually it is from TDC to this particular point, which is 90 minus 35. And your exhaust stroke, which was supposed to be starting from here BDC, it is now starting from here since exhaust wall has opened over here. So exhaust wall is now opened over here, and therefore exhaust process starts from here and it is completed till exhaust wall which is closing here. So the exhaust process is this 90 degree plus this 10 degree plus 35 degree. That is 90 plus 45 degree is your crank angle rotation required to complete the exhaust process. So theoretically it was 90, 90, 90, 90, but actually it is here you can see it is more than 90 initially the suction, less than 90 is your compression, less than 90 is your expansion, and more than 90 is your exhaust. So this is the difference between the theoretical wall timing diagram and actual wall timing diagram. So whenever question is asked about wall timing diagram, initially you have to explain, you have to draw the theoretical wall timing diagram and explain what this particular points are, and then you have to draw the actual wall timing diagram and explain why this particular things are happening depending on how much marks the question is being asked. If the question is asked for more marks, then you can give all the explanation regarding why this particular variation in the points are happening from dead center, why it has to be early, why it has to be late, etc., etc., all these things. Okay, why ignition has to be early, what will happen if it is advanced, what is happen if it is retarded, and all these things and its correlation with the speed, etc. All these things you can explain when you explain the timing diagram, that is wall timing diagram, if it is asked for more marks. If it is asked for less marks, your explanation can be reduced, but ensure that both the diagrams, that is the actual wall timing diagram and the theoretical wall timing, you are drawing it. Okay, so drawing both the actual and the theoretical wall timing diagram and the corresponding explanation with it will be the complete answer for the question. Explain the wall timing diagram. Now you can unmute yourself and ask the doubts. So I request everybody to unmute them and ask your doubt. Those who are having doubts, please. You can unmute your video plus audio. I have opened my video also now. I will hope I will be I'm visible now. Those who have doubts, please ask your doubts. Or as usual, I will ask questions then. So randomly, I will be asking questions to anybody. So by the time you prepare your questions, I will take 1 minute Pomodoro break. 1 minute. A Pomodoro break is a break where generally it is expected that the speaker should not speak in a stretch of a time more than a certain particular amount of time continuous, and for that she is supposed to take some amount of break. So now I've opened my video also. You can ask the questions. Yes, no questions. See, I always again and again telling you to become a good engineer. It is a very essential that you should ask questions. If you ask questions, you should be able to answer it.
Sir, hello,
Either two things that you understood nothing.
sir.
Shete, any doubt, please? Please.
Sir, can you explain once again?
What? What you want to explain me once again? Whole thing,
Yes, sir.
whole wall timing diagram.
Yes, sir.
Okay, 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 okay. I will explain you. Kunal again. So basically, a timing diagram is that diagram in which we graphically represent when walls are opening and closing. So we want to represent on a graph when the walls are going to open and close. Okay, and that particular graphical representation is what you call as a timing diagram. And if it is a four-stroke engine, we know that it is going to be walls, and we call it as a wall timing diagram. If it is a two-stroke engine, we know that it is ports, and therefore we call it as a port timing diagram. Correct? So wall timing diagram is related to four-stroke engine, and port timing diagram is related to two-stroke engine. Okay. Okay. Uh, moving ahead. Moving ahead. Now you can see this is a theoretical wall timing diagram. Why theoretical? Because theoretically we expect this thing to happen like this. Now, what all things we expect to happen like this means what? Means we have assumed certain thing. For example, we have assumed that combustion is going to happen instantaneously. So, if combustion is going to happen instantaneously on this particular diagram, the combustion will be only a one point. It will not be a certain. It will not be having some amount of angle corresponding to it, right? Because we are assuming that it is instantaneously. Correct. And we have assuming that the walls are going to open and close instantaneously. Okay. So again, the opening and closing will be also happening at a certain amount of time. Sorry, it will be denoted by only a single point. Correct. So that is how we have here at top dead center. We assume that the inlet wall is open, and when the inlet wall is open, suction is being started, and by the time it reaches bottom dead center, that is at the point when the piston reaches bottom dead center, we are going to close it. The inlet wall is going to close. Now the suction is going to end. Now both the walls are remaining closed. The mixture is going to get trapped, and the compression is going to start. The compression at TDC, the spark is given. Okay, is going to burn, it is going to start applying pressure on the piston, and the piston is going to push down from TDC to BDC. So when the piston is moving down, it is expansion stroke. Okay, and at the end of the expansion stroke, when the piston reaches BDC, the exhaust wall is going to open. So exhaust wall opens over here. Okay, the instant when the exhaust wall is open, exhaust gas rushes out to the exhaust manifold, and it is moving out, and this will happen till the exhaust wall is closed, and the exhaust wall is closed when the piston reaches top dead center. So here walls are opening and closing at dead center instantaneously. Along with that, combustion is also going to happen.
Hello. Sir, could you, sir?
Am I audible? Somebody confirm?
Yes,
Yes,
sir.
sir.
Okay. Due to some network problem, I think suddenly the presentation streaming was interrupted. Okay, no problem. I think I have cleared the point. Have I cleared the point for the doubt, whatever was being asked?
Yes, sir.
Okay. So now you can ask your doubts further. If you don't have any doubts, then I will start asking questions. Please, no doubts? No doubts?
Sir,
Ask your doubt.
hello. Hello.
Please.
Can you summarize all the today's teaching?
Yeah. Summarizing, basically, say what we have discussed today is that timing diagram. Okay. So initially we discussed the diesel engine cycle, that is diesel cycle, where we discussed about the difference between auto cycle and a diesel cycle. Okay. We discussed all the processes in the diesel cycle, like initially the suction was happening from 0 to 1, from 1 to 2 it was compression stroke, then 2 to 3 it was constant volume, sorry, constant pressure heat addition process, 3 to 4 it was the expansion, then 4 to 1 it was a constant volume heat rejection process, and 1 to 0 it was exhaust. Okay, so this was the diesel cycle, and then we compared the petrol cycle and the diesel cycle, and we said where the difference is actually. That is, the basic difference was at the point two. So in the auto cycle, the point two was corresponding to the spark point, and in the diesel cycle, the point two was corresponding to the injection point. Okay, so in the diesel cycle, the injection was supposed to happen, and injection means the flow of the fuel which was coming into the through the injector was broken up into droplets, and the droplets has to get dispersed in the combustion chamber. They have to pick the heat and they have to go for auto ignition, and this was taking time, and by the time the piston was supposed to move some degrees, and that is where instead of a constant volume we assumed that there was to be constant pressure. So then further we said it was going to that is 4 to 1 it was your expansion stroke, and then constant volume heat rejection, and from 1 to 0 it was uh, exhaust stroke. So that was the diesel cycle. So initially we compared, we discussed what is diesel cycle, then we compared the diesel cycle with petrol cycle, and we discussed what the difference between the two is. And then we went on to discuss what is timing diagram, and the different parameters related to timing diagram, related to wall opening and closing, wall operation, and why the change in the theoretical timing diagram and actual timing diagram we discussed, and then we discussed the actual timing diagram. Okay, then we discussed at what angles a certain wall has to be opened early, or at what angles the walls has to be closed late. Okay, in terms of both inlet wall and exhaust wall. Okay, and then we also discussed about the spark point, which was at TDC in the theoretical. It was before TDC, some 35 degrees in case of actual diagram. So we discussed why it is happening, and with respect to spark point, we discussed what is advancing of the spark and retarding of the spark. So this is a summary of what we have discussed today. I hope I have made the point. Yes, have I made the point?
Yes, sir.
Huh. So now, any doubt further?
No, sir.
Okay. May I go for asking the questions? Then we can go to for the remaining point. So, uh, so coming to Suhas Naste. Suhas Naste,
Yes,
can you
sir.
unmute yourself? Huh. Tell me what does mean by spark advance and what is spark retard? Please, Suhas.
Yes, sir.
Huh? What is spark advance and spark retarding?
Spark advance is the when we spark the
Mm-hmm.
before reaching the TDC we spark that is the spark advance and spark retard means
Means okay. Okay. Shubham Shingan, can you tell me what is spark advance or spark retarding? Shubham, Shubham, unmute yourself.
Yes, sir.
Ha. Explain what is spark advance and spark retarding. Unmute your voice as well as video so that I can see also. Now that I am also seeable to you, you can see me. Let you be also visible to me. Shubham, ha. Please,
Yes.
please tell me what is spark advance and spark retard.
Spark,
Yes, we have explained now what is spark advancing and spark retarding.
spark advancing.
Huh, what is it?
Uh,
Am I visible to you?
yes, sir.
Please, please tell me what is spark advance and spark retarding.
Spark advance.
See, students are leaving the meeting because I have start asking the questions. Huh? Okay. Misal, can you answer? Okay, thank you, Shubham. Misal, Shanesh. Please. Let your video be also visible to me. And please answer the question. What is spark advancing and spark retarding? Misal, unmute yourself and can you answer the question? Shanesh or Misal?
no sir.
Why? I've explained twice, thrice. Saurav Pawar, can you answer? Saurav Pawar? Somebody answer, those who are understood. Anybody who can answer this question? See, almost 35, 37 students are there. Somebody can answer. Somebody. Nobody?
Sir,
Okay. Huh? Somebody is trying. Can somebody try?
hello, sir.
Please.
Sir,
Please.
spark advance means the timing of ignition related to the position of piston, or maybe at TDC.
Spark. Okay. Good, Karande. So basically, confirm whether my PPT is visible. Karande, PPT is visible?
No, sir.
No. Okay. I will start presenting once again so that it is visible. Now I think it is visible.
Yes, sir.
Okay. So basically, see, it was supposed to happen at top dead center. The spark was supposed to happen at top dead center. But actually, when it is happening at a certain amount of time before top dead center. So this is some corresponding to design. We have fixed certain amount of angle over here. So let us suppose that it is 20 degree. That means it was supposed to happen over here. Or let us say it is 35 degree. It will be better. So this particular point is now, according to design, it has been finalized that the spark is supposed to happen at 35 degree. But as the spark, that is speed of the engine increases, what we have to do? The time available for combustion will remain same. Time required for combustion will remain same, but time available for combustion will become less, because the in lesser time the engine is rotating at higher speed, correct? Since the speed has increased, the net time available for the compression process or the expansion process goes on decreasing when the speed increases. That means what has to happen is this particular point has to be moved towards this side, that is the ignition has to become early. So in order to give sufficient time for combustion to happen, we have to make the spark instead of 35 degree by 40 degree. So we have advanced it. And on the contrary, suppose this particular engine has been designed for 1000 rpm. If you are going for running the engine at 2000 rpm, then you have to make it 40 degree. But on the contrary, instead of 1000 degree, you are going to run the engine at 500 rpm, then instead of 35 degree, this has to be going for 25 degree, where we say it is retarded. So moving this particular point towards left side is what you call as advancing, and moving this particular point towards the right side is what you call as retarding. Okay, so the advancing means giving the spark early, and retarding means giving the spark late. With respect to which? With respect to the design value. So we have a design value over here, and with respect to this, whether we are going to give spark early or late. If we are going to give it early, we say spark is advanced. If you are going to give it late, then we say spark is yes. Can anybody? If you are giving the late, what we call it as? Spark is
Retarded.
Retarded. Correct. So either we advance or retard. When to advance? When we increase the speed of the engine. So see, if the vehicle is going on a straight road without any slope or a very flat road, highway, engine will be running at a certain speed. But suppose suddenly the vehicle is going up a hill, what will happen to accelerator? We will go give more accelerator and increase the speed of the engine. When the speed of the engine is increased, at that time the ignition has to be advanced, correct, than this particular value. And on the contrary, if you are going down a hill, You don't require that much power. So you will try to remove the power foot from your accelerator. Why? You don't want that much power. So when the speed is going to decrease, then the ignition has to be retarded. Ignition has to be retarded. I hope the point advancing and retarding is clear to everybody. Can somebody confirm it? Can somebody confirm it? Can somebody confirm it?
Yes, sir.
Okay. Any other doubt related to timing diagram for a two-stroke and a four-stroke SI engine? Any other? Yes. Any other doubt? Any other doubt? If you have, you can ask, or else I will give you the second question for your assignment. I'm writing the question in the chat box. The question is, explain the timing diagram. You can take it down for or with a neat sketch. Initially write with a neat sketch. With neat sketches, comma, explain the timing diagram for high speed and low speed four-stroke engine. So I will once again read the question. With neat sketches, explain the timing diagram for high speed and low speed four-stroke engine. So the figure will be similar. So initially you have to go for a theoretical timing diagram. Then you have to draw a actual timing diagram. Then you have to compare this two, state the difference. So let this particular question be asked for 10 marks. So corresponding to the 10 marks, you have to make it elaborate. Okay, it's 10 marks. Okay, so with neat sketch, explain the timing diagram for high speed and low speed engine. So then you have to draw two actual timing diagrams, one for a low speed engine and one for a high speed engine. So when you are drawing a low speed engine timing diagram, the angles will be lesser. When you draw the high speed engine timing diagram, the angles will be more. Okay, so go search it and find the correct answers for this particular values and draw separate actual timing diagram for a low speed engine and a high speed engine. So I have cleared the points related to timing diagram. Everybody has understood the wall timing diagram for a SI engine. Still, it is open for clearing the doubts. And if you have understood everything and you don't have any doubt, then you can, if you are not given the attendance till now, you give your attendance and you can leave. So you give your attendance on the chat, and if you have cleared all the doubts, if you don't have any doubt, you can give your attendance and you may leave. Don't give repeatedly many times same number. Already if you are given at the start, not necessary again. And you may leave the meet. And if you have any doubts, please ask. Anybody having any doubt? Please ask. Please.
Can you send recording of the picture?
Yeah, I may. Okay, no problem. I will send you the recordings on the WhatsApp group. I will send it. No problem. Okay, thank you.
Okay.
Any doubts, please? If you don't have the doubts, please mark your attendance in the chat box and then we email you.